Hello, my name is Ali Yahya and I'm the VP of IonFlux product at Fluxion Biosciences. I would like to thank everybody for attending this webinar. For questions, please use the question box and I will attempt to answer them at the end of the session. Today I will be talking about advanced fluidics provided by the IonFlux system necessary for unique high throughput voltage and ligand-gated assays. The outline of this webinar is as follows. First, I will give you a background of the IonFlux technology and what makes it unique among automated patch clamp devices. Second, I will talk about the flexibility in setting up assays with its enhanced fluidic control. And third, I will show you some customer data which was presented recently in different webinars and conferences. The data will look at GABA-PAM screening assays, nicotinic receptors validation, and NAV 1.8 screens. To start, this is a primer about Fluxion Biosciences. The company was founded in 2005. Our headquarters are in South San Francisco, California. The company won 5 NIH grants and 2 R&D 100 awards for BioFlux in 2008 and IonFlux in 2010. We have 3 main product lines, all based on microfluidics technology. BioFlux, used for live cell imaging under flow. IonFlux and IsoFlux, a microfluidics-based CTC detection system. The IonFlux is, in simple terms, an automated patch clamp system which is based on a unique in-plate liquid handling or movement strategy. The system does not require a complicated liquid handler to move solutions and hence has a footprint of a simple plate reader. It comes in 2 main flavors, IonFlux 16 with 16 amplifiers and IonFlux HT with 64 amplifiers. Both systems are based on the same technology and share the same assays. The lack of a liquid handler allows both the IonFlux 16 and the HT to be not only extremely flexible in fluidics, but also quite competitive in price. The lack of dedicated liquid handling is actually the end result of the IonFlux unique ability to move solutions inside of the recording plate itself. The machine uses standard SPS plate formats, 96 well for IF16 and 384 well for IF-HT. The bottom of the plate has been replaced with an intricate laminar flow system, providing an integrated cell and compound delivery system. Looking at the bottom of the IonFlux plate in more detail, the plate is divided into patterns. Zooming into one of these patterns and flipping it to the top, the pattern is composed of 12 wells. 2 independent recording wells are connected to separate amplifiers. These recording wells are called traps and would contain the intracellular solution. An inlet well, where cells in extracellular solution are introduced, and an out or waste well. And 8 different wells where different compounds and solutions can be added. We have 32 experimental patterns per IonFlux HT plate and 8 patterns per IonFlux 16 plate. The design of the plate and the intra-movement of all solutions allows for independent compounds conduits, hence no mixing, no cross-contamination, no pipetting delays, and no electrode-compound contact. Looking closely at the mechanism of action, once plate is filled, it is introduced into the machine. The start of the assay begins with priming of the microfluidics. After that, the cells with extracellular solutions start flowing through the main chamber until trapping occurs and seals are formed. Extra suction opens the cells and recording begins in whole cell patch clamping mode. A typical experiment would involve opening the compound pneumatic valves, allowing the release of the compounds into the main channel, flowing continuously towards the cells. The independent control of these compound inlets provides fast and successive compound additions as well as continuous washing steps in between the compound additions. Consider that these steps are not really steps, but more like washing gaps in between the compound release from their inlets. This will become clearer later on. It is important to note that the reliance on pneumatics instead of physical compound movement provides the parallel release of all compounds at the exact time. Hence, 1 experiment or 32 experiments will take exactly the same time to complete, allowing IonFlux assays to complete very quickly. One customer reported completing 500 compounds per day with close to 8,000 data points. Let's look back at the solution movement and control of that within the plate. The IonFlux software provides extensive graphical control over the delivery of compounds and solutions. The start and end of the release of a specific compound is simply drawn in the software. Separating the steps would mean washing of the cells. The longer or shorter the distance between the steps, the longer or shorter the wash step. In fact, we can get the steps so close to each other that no washing occurs. Here we step from one compound to another instantly. Again, all this is happening in parallel within the plate and with continuous flow. So we are not adding one compound, leaving it there, then coming back with another compound like in other instruments. We are continuously flowing one compound until another takes over. Although these steps are of the same size here, you do have complete control over their length and can even superimpose them. In fact, with the lines, when the lines are superimposed, we can have two compounds flowing at the same time. This ability shows off the true capability of the system's fluidics. To explain this point, although we can have two compounds flowing, the cells only see the compound flowing from the well closest to them. The higher the number, the closer the compound. In this case, compound number 3. Then, as time progresses, we would have an interruption in the flow, so the other compound would fall on the cells nearly instantly. This flexibility in compound displacement provides extensive capability in the development of difficult ligand-gated assays, such as we will see later on. Another very important effect of the fluidics with IonFlux, especially related to the ability to provide continuous flow solution, is the ability to get superimposable currents when the same concentration of agonist is added. This is especially seen with GABA. These superimposed currents show differences in the total value of the current, but within the same recording, the sweep-to-sweep variability is minimal. Here we see two recording wells receiving 10 micromolar GABA. This stability is quite important, as you see later on, in doing complex assays such as PAM screens. This can be observed more clearly with this IT plot. Just to explain, this is a plot of values seen by placing cursors in the software at specific location in the sweep run. Within the sweeps, two cursors are placed, one before the addition of GABA and one after it. The values are subtracted. When GABA is added, a response is measured and a negative point is recorded. When wash steps are followed, no response is seen and a zero value is recorded. This repeatability and consistency of response was also observed at Eurofins during their system validation. The data was presented by Michael Donio in a webinar last year. The slides above show consistent and reproducible response from two GABA-A cell lines, alpha-1 beta-3 gamma-2 and alpha-5 beta-3 gamma-2. Of course, in screening conditions, repeatability of response within an experiment is just as important as reliability of response from day to day. Michael showed this slide about the EC50 of GABA on alpha-1 beta-3 gamma-2 for over 3 days. The variability in the measurement was minimal, providing the basis of a very reliable assay. Michael also showed a very reliable EC50 measurement of PAM effects on GABA receptors. This slide shows EC50 of diazepam over 3 days, again showing little variability in measurements. Of course, once PAM effects were established, antagonism of the effect can also be obtained. He showed the effect of flumazenil on diazepam. The current from the GABA receptor was enhanced with the addition of diazepam, then gradually decreased by the addition of flumazenil. Again, the experiments showed consistency over 3 days. Since these experiments are done in sequence, addition of GABA for baseline, then addition of PAM for another baseline, followed by addition of the antagonist, the importance of a steady and repeatable baseline comes to light. We have established that pneumatic control and a plate-based microfluidics design allows the IonFlux to have high flexibility in sequentially changing extracellular solution with no wash step in between. This flexibility in liquid exchange allows for some other complicated and interesting assays to be performed. Looking back at the example compound addition map from before and considering that the activated GABA-A receptor current shows a fast activation, followed by a slow deactivation, it is possible to sequentially increase the agonist dose faster than the rate of deactivation, effectively increasing the activation of current in a staircase effect. If all timed correctly, a current staircase would be seen within the same sweep in response to increase in agonist concentration. An example of this staircase activation is shown here. The receptor was activated by 1 micromolar GABA, followed by 3 micromolar GABA, then 10 micromolar. The compounds are applied for 2 seconds at each concentration. Here we have response from 2 wells. An interesting part of this assay is the ability to obtain a quick EC50 from a single sweep. Again, this is not the calculated current versus time achieved by obtaining multiple sweeps. This is a staircase increase in current within the same sweep. The perfect timing and fluidic control that the IonFlux provides allows changes in solutions within a sweep across the whole plate, all at the same time. To show the potentiating effect of PAMs, a similar experiment is conducted where a constant application of modulator is added when compared to control. Here we have the same staircase GABA activation with and without co-application of 3 micromolar diazepam, clearly showing the expected allosteric shift in current magnitude. This can become more complicated. Another example here is an overlay of DMSO control, GABA for 8 seconds, green line, GABA for 4 seconds, then GABA plus diazepam for 8 seconds, blue line, and GABA for 4 seconds followed by GABA with a blocker, here picrotoxin, for 8 seconds. All the above experiments were done within the same plate and at the same time. Again with all the steps within the same sweeps. This technique of adding different compounds while the channel is open was implemented by Juha Kimmonen from Pfizer and Nucentis and was presented in also another webinar last year. Juha utilized the stable repeatability of current and open channel compound addition in his PAM screening assay. He showed a GAB-PAM screening assay that was both complicated and fast. He presented the compound addition map, showing how the compounds were added during the experiment. A zoom in shows that he set up compound additions overlaps. Here showing the overlap between compound 4, 6, and 7. Again, the cells only see the solution coming from the compound well nearest to them. In this case, they will see solution from well number 7, then 6, then 4. As soon as 4, 3, and 1 are done, they will see 7 again. As seen in the slide, Juha utilized the ability to add compounds while the channel is open. He showed the opening of the channels with GABA, first solution, then followed by the addition of different compounds. Black showing the effect of GABA and DMSO, yellow the effect of diazepam, and red the effect of another PAM. To the right, the additions were a bit more complex, allowing for a dose response of the PAM effect. Using the software Gene Data Screener, which can import and analyze the IonFlux data, he was able to analyze large data structures from the IonFlux. Here is a trace showing the results from one of those experiments that were outlined before with the baseline addition of GABA, then followed by the open channel PAM effect. The blue boxes to the right show a heat map of the IonFlux plate. A zoom into the data shows the PAM effect from before, the baseline effect followed by a single dose effect of PAM, then a dose response, all in sequence with incredible consistency in the data. Juha also discussed assays for screening compounds against NAV 1.8. Now here the cells were subjected to continuous flow from compound well number 8 with gaps to allow access to the other compounds. When the gap occurs, the cells will see the compounds. Once the gap is over, they will see 8 again. Compound 8 here acting as a protective wash solution. This same assay can also be used for NMDA and for other much more complicated ligand channels and receptors. A zoom into this shows the ability to overlap the additions of the compounds to allow instant exchange from one solution to another. Here is a trace with multiple compounds added, some sticky and some not. The effects of the compounds are seen by dose-related block of the current and the subsequent recovery, of course if the compound allows for it. If you look at the red trace, you will notice that the currents with no compounds added are quite stable. Now going back to urofins, David Buey showed validation data for several nicotinic channels at the ion channel retreat last year. Again, the continuous flow ability of the IonFlux allowed for repeated activation of nicotinic receptors using acetylcholine with high successive current stability and no addition of any enzyme. The plot to the left shows successive normalized currents from 4 subunits including alpha 7. Just like with GABA receptors, repeating the experiments over several days yielded consistent, nearly superimposable results. As with Juha's demonstration, David showed open channel block of alpha-4 beta-2 receptors utilizing the same technique of applying successive compounds while the channels are open. Here activating the channel with 30 micromolar ACH, then blocking with mecamylamine. David also showed the effects of PAM on different subunits of the nicotinic receptors. LY2087-101 showed different effects on different subunits, while PNU 120-596 showing measurable effect only on alpha 7. The control over fluidic additions allowed David to increase the frequency of acetylcholine additions and measure the desensitization effect of alpha-4 beta-2. Again, no enzymes are used, simply continuous flow and short additions. As the frequency of additions increased, as desensitization increased. Also, David showed the recovery of the current from desensitization. The experiment above activates the current, then applies a second dose at an increasing distance from the first. Plotting the response shows the recovery curve to the bottom left. Bottom right shows the assay involved. These experiments are done in parallel with very controlled exchange of solution. Okay, now to summarize, the IonFlux system, equipped with its unique liquid exchange and continuous flow system, provides an excellent platform for complex assays. The ability to provide a consecutive and fast switch from one compound to another, or to serially increase compound concentrations with no wash steps or liquid stacking problem, gives the platform the unique edge and speed a complex assay requires. I would like to thank Juha Kimonen from Pfizer, Michael Donio, and Haeyang David